Our topic for today is TCP/IP and the Internet. It's really an exciting topic. TCP/IP and the Internet is where everything is happening these days. It's an extremely exciting topic. We're going to learn how all this stuff works. We're going to talk about TCP/IP specifically. What is it? You've heard the letters. What do they mean? We're going to talk about something called IP addresses. IP addresses, what they are and what they look like and why they're important. We're going to talk about something called routers. Routers. And we'll talk about the Internet, what it is, and basically how it works. We're going to talk about something within TCP/IP, which is actually a suite of protocols and applications called Telnet, and specifically a specific flavor of Telnet called TN3270. We're going to talk about something called FTP, File Transfer Protocol. SMTP, Simple Mail Transfer Protocol. We're going to talk about the World Wide Web and how that works. And we'll talk a little bit about HTML, Hypertext Markup Language, what that looks like and how that fits into the picture. Let's start by talking about TCP/IP. TCP/IP, what does it stand for? Transmission Control Protocol, Internet Protocol. Transmission Control Protocol, Internet Protocol. It is a communications protocol suite developed under contract from the U.S. Department of Defense to internetwork dissimilar systems. Now, when I first got acquainted with TCP/IP, which hasn't been that many years ago, but I'd heard about it before that, it kind of bothered me because the word protocol appeared twice in TCP/IP. And I said, you know, there's something wrong here. I'm used to things where there's a single protocol within an architecture, but here I see the word protocol twice. And then once I understood TCP/IP, I said, oh yeah, there really are two protocols and two things going on, and we're going to learn what those things are today. A little history on TCP/IP and internetworking. Back in 1957, the Advanced Research Projects Agency, called ARPA, was formed within the Department of Defense. Anybody remember something of great significance that occurred in 1957, which was one of the driving reasons for the formation of this? Sputnik. Russians launched Sputnik, and we got concerned. We were behind the ball. So we got real interested in technology then. It was a good thing. In 1969, something called the ARPANET was commissioned by the Department of Defense for research into networking. Now, the interesting thing behind all of this stuff is TCP/IP, you sort of associate it with Unix machines and, Berkeley and long hairs and, that sort of stuff. Well, actually, most of this was commissioned by the Department of Defense. And the reason that it was commissioned was they wanted to build a network that could survive some sort of an attack, like a nuclear attack or in a war. They wanted a network that was resilient enough and that could work even if parts of it were knocked out. And they also wanted to interconnect dissimilar computing systems, because we talked about that in the past, how even the Department of Defense, the Army, the Navy, the Marines, they all had, even within a single branch like the Air Force, there were different computing systems, and they needed to intercommunicate, to interconnect. So we needed some standard, something common that would allow that to happen. In 1982, ARPANET began using TCP/IP. So we kind of think of TCP/IP as a fairly recent thing, hot topic now. It's been around at least 16 years. In 1982, ARPANET began using TCP/IP. It was using other protocols prior to 1982. In 1986, something called the IETF, the Internet Engineering Task Force, was formed. And that was an important body because they were very instrumental in setting standards. And standards is the thing that makes all of this work. So there's our OSI model, our 7-layer stack. How does TCP/IP stack up against the OSI model? Well, it does stack up, but TCP/IP, rather than being a 7-layer model, is a 4-layer model. The lowest level is called the network access layer, and it corresponds to the physical data link and part of the network layers in the OSI model. Now, over here on the right-hand column, I'm going to show examples. I'm going to tell you what parts of TCP/IP fall within the 4 layers. Notice there are none, because TCP/IP makes no definition at the network access layer. It will use anything. Because remember, down at that layer, we're talking about getting a message from one point to another. So TCP/IP will use frame relay, it will use ATM, it will use X.25, it can use token ring, it can use Ethernet, it can use lease lines, it can use dial lines, all of those things we've talked about in the last 4 weeks. And it doesn't care. It doesn't care what is the transport, what gets it from one point to another. Now, moving up the stack is the internet level, and that is the IP part of TCP/IP. The internet layer is concerned with routing, with getting data from one point to another point, perhaps through multiple nodes. The next layer is what's called host-to-host, host-to-host. That's the TCP part of it. That layer is concerned with making sure that all the data that's sent from one computer system is received correctly and in the right order at the other computer system that it's being sent to. And it also acts as an interface to the highest level, which is called process. On the OSI model, that's application and presentation. And there are some applications that we're going to talk about today, some specific applications within this suite. Telnet, FTP, SMTP, and HTTP. And you say, where have I seen those letters before? Well, it's on your browser. You know, that funny little thing, that http:// stuff. We'll talk about that. Let's start down at the bottom now and talk about IP first. IP. Internetwork protocol. Internetwork protocol. It is a connectionless service to enable devices to communicate across one or more networks. Now, there's an interesting word in there, I think, connectionless. You know, connectionless, you know, what do you mean by connectionless? We've talked about some connection-oriented things, but what is this connectionless thing? Let me give you an example. You know what connectionless is. Suppose you have a letter that you want to mail. You want to mail to a friend in Dallas, because I love Dallas and I love Texas. So you take that letter, you address it. So the letter contains on it the address of where it's going. You put it in the mailbox. And then a postal person, must be politically correct, a postal person takes the letter. It goes into the mail system. You know, it flows by train, it flows by airplane, it goes by trucks, it goes by carrier, it goes all over the place. Where you want to get is to the recipient there in Dallas, and if you're lucky and everything works right, that person gets it. Okay? Connectionless. Why is it connectionless? Did you ever have a direct connection with that person to receive the letter? No. You put it in the system, and it got there the best way it could. That's connectionless. IP is a connectionless protocol. We take data, we encapsulate it with an IP. We put it in the network and say, network, get it there the best way you can. Connectionless. Contrast that to X.25. Remember we talked about X.25 and it used a virtual circuit? It is connection-oriented. When we make a phone call, that's connection-oriented. We establish a connection, we use the connection, and at the end, we tear down the connection. Or if it's in the case of a leased line or a permanent virtual circuit and frame relay or ATM, it's there all the time. So let's look at how this thing works, the Internet protocol. If we want to send something from point 1 over here to point 64. I said it's connectionless. It uses something called IP addresses to get it there. IP addresses. The pink things, in this case, are routers. This is a network, looks very similar to that X.25 network, doesn't it? Well, I didn't have time to draw a lot of pictures, so I kind of reused it, changed the colors. Where these were pads before, in this environment there are routers. Routers, well, what's a router? A router is a device that understands IP addresses. Let's talk about IP addresses. What are IP addresses? Well, they're 32 bits in length. 32 bits in length. And they are represented as what is called dotted decimal. There's some other terms that are used, but the most common one I've heard is called dotted decimal. Looks like that. Somebody calls you up and they say, what's your IP address? And you say, 165.176.32.4. Well, you know, where do the numbers come from? IP addresses are 32 bits in length. We can divide that into 4 bytes of 8 bits each. If we take a single byte, which is 8 bits, take the binary value of that and convert it to decimal, those of you who know how to do that, or you can use a calculator, we get a number that ranges from 0 to 255. These 4 numbers represent the decimal value of those 4 bytes of the IP address. An organization called the INTERNIC, the Internetwork Information Center, controls internet addresses and domain names. I said, what are domain names? Well, we're going to talk about those in a minute. Now, there is a problem with IP addresses. Given 32 bits, there are numbers from 0 to somewhere around 4 billion and some change, a couple hundred million. I worked it out. It's 2 to the 32 minus 1. Okay, it's around 4 billion. We're running out of IP addresses. You say 4 billion and we're running out? Well, yeah, this is a worldwide thing. You know, how many computers are there in the United States alone? When you look at it on a worldwide basis, we're running out of IP addresses. Some ranges of IP addresses are not used. They're reserved for certain things. It's a major problem. It is a major problem because of where TCP IP having become the de facto standard used around the world. So there is a project underway to expand the IP address size from 32 bits to 128 bits. Now, that's going to be a tough conversion. I don't know how, that's one of the reasons it hadn't happened. When you consider all the routers and all the TCP IP stacks around the world, and now you're going to change a basic element of it, the IP address, the length of it from 4 bytes to 32, from 4 bytes to 128 bits, okay, which is 16 bytes. That's going to be a major conversion, but it has to happen. And there's a project underway to do that. Well, routers are the things that understand IP addresses. A router is an internetworking device that connects 2 or more networks. Routers are really cool devices. And I know cool is kind of a dated term, but hey, I'm a dated guy. They can do all kinds of things. I mean, this is a picture of our 7513 router made by Cisco Systems down in the computer room. And it's kind of sad that it's sort of a bland-looking box. I mean, routers they don't have lights, they don't blink, they don't do, you know, like old mainframes like IBM 360 50s and 65s, and those of you who worked on 145s and all that, you know, it had the light bars and the lights blinked, and you know, it was impressive, and you brought people in on a tour and they, wow, this is neat. Now everything's just kind of there with, you know, like little red lights blinking or something or nothing. You know, nothing here, but it is really a cool device because it understands IP and it knows how to route things, and we're going to see how it does it. It can talk all kinds of protocols. It can talk frame relay, ATM, X.25. It can talk leased lines. It can talk something called HDLC. It can talk Ethernet. It can talk token ring. I haven't found anything yet, any sort of a network protocol that a router couldn't handle. They're really amazing. You can take a router, have an Ethernet link coming into a router, and data flowing into it on the router. On the other side, it comes in token ring, goes out Ethernet. Or it comes in frame relay and goes out Ethernet. They're just amazing, wonderful, cool devices. Two major vendors, and I hope I don't leave anybody out, but the two, we mostly have routers that are built by a company called Cisco Systems. And if you bought stock in Cisco, 5-10 years ago, you probably wouldn't be working today if you held on to it. It's a great little company, grown quite a bit. And the other major vendor is one called Bay Systems. We use Cisco Systems within the state. So now, let's see how this thing works. Let's see, as we talked about earlier, if we have some data up there at that computer, which is address 165.176.32.1, that's its IP address, and it wants to send some data over here to 165.176, and the glasses got the wrong way there, .32.64. This is all the same network. See, the first three dots are the same. And we have all these little nodes in between that are connected, and they could be connected, however, Ethernet or token ring or frame relay or ATM or, however they're connected. So how does it work? Well, that computer up there at .1 sends some data to the router that it is connected to, which is .5. And part of that data is the address. Just like that envelope, when we put it in the mailbox, we had the address of where it's going to go. The data contains the address of where it's going to go. It sends it to that router. That router looks at the IP address. And it has something called a route table. A route table. This is just representative of what a route table would look like. In other words, the table's composed of two parts. To get to this IP address, you go to this IP address. Now notice in the route table, there isn't a map of the complete route. Like to get from 5 to 60, there isn't a complete map. Because all a router cares about is passing the buck. Routers do not operate on the buck stops here. Routers operate on give it to somebody else and it's somebody else's problem. Okay? Pass it on. Get it away from me. So we send this packet, this IP packet, to the router, and the router looks at the IP address, the destination, which is 165.176.32.64, and it looks up in its route table. There are two kinds of routes. One's called static routes, which are defined by programmers saying, this IP address, you go here. Most of the routes are dynamic. That is, the routers intercommunicate with each other. They talk to each other, and they exchange information about routes. So these routing tables are constantly being updated on a dynamic basis. And that is a whole technology within itself. So we take this address where we want to go to, and we look it up in the table. We're looking for .64. 15, nope. 25, nope. 40, nope. Didn't find it. There's what's called a default route. That is, if I can't find an IP address that I'm looking for in my table, I'm going to pass the buck. I'm going to send it here. So in this case, we didn't find that address in the table, so it's going to send it to the router at 165.176.32.10. Okay? Now, that router doesn't know that that's going to get it to its destination, but it says, hey, that's the only thing I know. I don't know where it goes, but I'll hand it to this guy. Maybe he knows where it goes. So the packet is passed along to the next router at .10. That router gets the packet, looks at the destination IP address. It has a route table. .64. It looks in its table. It doesn't know where it goes, so it has a default route to go to 165.176.32.25. Hey, what if somebody messed up and had an entry in here that said, if the default route was to go back to 5? what would happen then? You know, they just keep throwing it back and forth till there was some timeout that occurred. And things like that happen. So, you know, people who program routers have to be careful about that sort of stuff. But in this case, we didn't find it. The default is to send it to 25. Send it to 25. So it does. Let's step back for just a minute, go back to the OSI model. How's all this stuff working? Well, we came from that computer at dot 1 down the OSI model, although we know in TCP IP this is broken into 4 layers as opposed to 7, but you can kind of correlate them. So we know, just like we've seen before, we come down the stack, across the physical layer. Now we're back at the router. The router goes up to layer 3. A router is called a layer 3 device, a layer 3 device. And so the router looks at because it's routing things, looks at it at the network layer, and then sends things along. And we may go through multiple of these, as we've seen already, and we're going to see exactly how this whole thing works, until it gets to where it's going to go. Okay? So now, let's see how that packet gets to where it wants to go. Well, we already saw it sent it to 5, it sent it to 10, it sent it to 25. Oh, and then 25 sent it to 50. And maybe 25 had a dynamic route statement in there that said, oh, I know, to get to 64, go to 50, perhaps. Or maybe 25 said, I don't know how to get to 64, so I'm passing it on to 50. 50 passes it to 60. More than likely, 50 definitely knows where that is, because adjacent routers kind of know a lot about each other. And then eventually gets to 64. Okay? IP, the Internet Protocol. It's how all of the stuff that you're doing, web pages, email, all of that stuff runs on IP. Works like that. Well, that network that we saw out there, it forms part of something called the Internet. And we all hear about the Internet and kind of have these, I sort of had a visual picture in my mind of like a big pipe was the Internet. What is it? How does it work? Because I was really, the first time I ever did it, and I'm out there surfing the net, and boy, here I'm in Australia, and now I'm in the United Kingdom, and now I'm in Belgium, and just all over the world. And it just, the first time I did it, I couldn't believe it. It just blew me away. And I said, how does this thing work? Well, it works through the Internet. The Internet is simply the interconnection of many individual networks. They're interconnected. They're interconnected. Well, what's the hierarchy? How are they interconnected? Well, the first connection occurs at something called an ISP, an Internet Service Provider. We here at DIT use an Internet Service Provider called VisiNet. There are bunches of them. Errol's, AOL, tons of them out there. Here's a map showing the yellow dots show ISP home office locations. Look at the East Coast and look at the West Coast, where most of the activity is, especially in the Northeast. Notice up in Northern Virginia, there's lots of yellow dots. If you were at the agency meeting yesterday, our new Secretary of Technology talked about technology in Virginia, and that we were, Virginia's kind of getting a name as the Silicon Valley of the East. And that's really true. If you go up to Northern Virginia, there are a bunch of Internet service providers up there. AOL is at Vienna, Virginia. I took a router class a couple of years up there, and the hotel I was staying in happened to be right across the street from AOL, and I was an AOL user at the time. There's some other things neat that happen in Virginia that concern the Internet. But the first level is the Internet Service Provider. That's somebody that you connect to that is connected to the Internet, that provides you service. The ISPs connect to regional networks through what are called network access points. They all interconnect. These are also known as metropolitan area exchanges, also known as MEIs. And there is a MEI East. You can see where I'm going. It's in Washington, D.C. It's actually in Northern Virginia. You know, they say metropolitan Washington, D.C. Hey, it's Northern Virginia, okay? May East is in Northern Virginia. And yeah, there is a May West. And that's near San Francisco. It's actually in Silicon Valley. Okay, a May East and a May West. A metropolitan area exchange. Well, you know, so what does all this look like? Here's our map within all our internet service providers, and they have links that are going out to their customers, and they're connected to regional networks. Well, now somehow they all have to talk to each other so this whole thing works, so that you can talk to anyone at any time. And they connect through these metropolitan area exchanges. We said there was one in San Francisco, and there's one in Washington. I should have changed this to say Northern Virginia, but you know, the literature says Washington, so we'll go with that. And those two are linked by very high-speed communications links, very high speed. Now, there are some smaller Mays, and they are located at Los Angeles, Dallas, Houston, two in Texas, all right, New York, and Chicago. The Mays system is run by WorldCom, you know, the company that's gobbling up MCI. Okay, WorldCom runs this. So all the ISPs connect to these Mays where there are big routers. So this is how all the networks are interconnected, how you get from DIT to our internet service provider to a regional network to a metropolitan area exchange. Hey, and the other thing that's going on here is, like here at May East, Washington, that has links over to Europe, across the ocean. And then May West has links out into Australia and the Pacific region. So that is the internet. So who owns it? Well, not any one person owns it. It's collectively run. And it forms a global internet. A global internet. Because if you've been out surfing on the web, you know that you can be here, and then you can be in the United Kingdom, you can be in Australia. I had a pen pal in Australia for a couple of years. It was quite exciting to learn about what they were doing there. So who runs the internet? A whole bunch of people run the internet. Here's some of the people. The Internet Society, the Internic, the World Wide Web, Web Consortium, governments are involved, content developers, including maybe you, a whole bunch of organizations. And they run it as a collective effort. Internet host. All the computers that have IP addresses that are connected to the internet are called internet hosts, and the growth has been phenomenal. Statistics as of 1997, 19 million hosts connected to the internet worldwide, 19 million. That's a lot of computers connected to an internetwork that you can access. There are two other kinds of nets you may have heard of. One is called an intranet. An intranet. That is an in-house private network for internal users. We have an intranet here at DIT where we have internal stuff. We don't want people from the internet, from, you know, John Q. Public or Australia or Germany or wherever, to see that information. So we have an intranet, our own little internal network that is protected, that only we can get to, where we store information and make it available. These presentations are stored on the intranet. And I'll mention very quickly the little handouts I've been doing, which have terminology and acronyms. There will be an entry on the intranet site where all of these are combined into one. Because, you know, if you keep these and you want to look up a term, you have to say, well, let's see, what presentation was that in? But it will be a combined one in alphabetical order. And that will be out on our intranet. Kathy Stone maintains our intranet here at DIT. Now, there's another term that's kind of come about fairly recently called extranets. You know, why do we have to keep making up all these terms? What is an extranet? Well, it's an intranet with controlled access. That is, sometimes there are other people who are not within your organization who you want to be able to access your private information that you don't want known to the world. Case in point might be a company who is collaborating with someone on designing something. Let's say they're working with some sort of a design consulting firm, and they have documents and information stored on their intranet relative to this project, and so they grant these other users outside of their organization access to their intranet. That's called an extranet, an extranet. So that's IP and the internet. Let's move up the stack now and talk about TCP. The TCP is kind of like the Rodney Dangerfield. I mean, it does a lot of good stuff, but there's not a lot to say about it other than it's transmission control protocol, and it provides transport functions and ensures that data is correctly sent and received. That's what it does. It provides interfaces to the applications. That's TCP. It does a lot of good stuff, but doesn't get a lot of good press. So now let's move up to the guys who get all the press, the applications, the processes. Telnet, FTP, SMTP, and HTTP. Telnet. What is Telnet? Telnet is a TCP IP defined function that allows you from one computer to log on to a remote computer. I'm sitting on this computer, and then through some connection using TCP IP, I establish a session on another computer, sign on to that computer so that I can do work or play. That's Telnet. Now, we're interested here at DIT in a specific flavor of Telnet, a specific version of Telnet called TN3270. TN3270. Let's step back in time to my time, to IBM SNA. IBM SNA, Systems Network Architecture, was introduced in 1974. I remember it like it was yesterday. Went down to Raleigh for the big presentation, and they talked about these, hey, we're going to run at line speeds of 9.6 and maybe 19.2, and we're saying, wow, this is great. Okay? We have a very large investment in SNA within the state. And SNA is not going away, contrary to popular opinion. Part of it, something called SDLC, we'll see what that is going to go away, but SNA isn't. In the SNA architecture, SNA was an architecture defined by IBM in 1974 that defined how IBM devices would communicate, all the way from the terminal to the endpoint. And it had an architecture, a stack, and all that sort of stuff. But it was proprietary. It was owned by IBM. The terminals out there were called 3270s, and there are various flavors of them. There's 3278s and 3279s, but they're known as the 3270 family of terminals. The TN3270, there's where the 3270 comes from. It's a type of terminal. Has certain characteristics, certain screen sizes, certain ways that it operates. Now, the communications protocol that was used to connect those terminals through the network was called SDLC, Synchronous Data Link Control. We still run a lot of SDLC around here. Somewhere in excess of 400 lines, communications lines, all around the state, we run SDLC. My goal in life is to reduce that number to as small as possible. I want to move to frame relay and ATM and other technologies. That's my goal in life. We'll see how well that comes about. It's dependent on the agencies. It talks through, the modem, the matrix switch, the front end. In the front-end processor, there's something called NCP, Network Control Program runs. Okay? And SNA was kind of a radical departure because it offloaded this front-end processor thing. That was kind of a radical thing. I remember all in the 70s we were saying, oh, well, it'll never work, it'll never work. Because prior to that, the mainframe did all the work. It did all the communications, error recovery, and all of that stuff. And people talked a lot about front-end processors, and some of us were skeptical, but I mean, it's reality. It talks to something in the mainframe called VTAM, Virtual Telecommunications Access Method. Why do I talk about all this? Because VTAM and SNA are going to be around for a long time. SDLC is going to go away, or will minimize anyway. But these other things are going to stick around. Now, that's the way. We've got a lot of lines that look like this. We know that there's, MUXs, IDNXs, and central office hubbing and all that stuff. We won't go into that. But how can we connect? Now we go out, we rip out all those 3270 terminals, and we put in PCs, and we put TCP IP stacks on them. And now the first thing that people say is, gee, I need to get to DIT to do my SIPs and CARs. How do I do that? Well, through this TN3270. Over on the PC, there's something called a TN3270 client. It's part of TCP IP. There's a TCP IP stack on the PC, and we have this application called TN3270. It connects, in our case at DIT, through the network, through our frame relay network, using routers. Our customers have routers, and let's say in this case they're running a LAN with the PCs attached to the router. Runs through frame relay, gets down here to DIT, to our router, and it hits something called a firewall. What's a firewall? Firewall is a device that controls the access to a network, one or more networks. And what the firewall does is it has rules in it that basically say, I will let these IP addresses go through the firewall to the other side. If they're not rules, I won't let the IP address go through. This is to keep people from the internet, because we have a connection, as we'll see, to our router, to the internet, to keep people in the internet from hacking in to our enterprise servers, where all the good data is, and getting at information they shouldn't be. Although we have security over here, this is a double layer of security, and it's called a firewall. And it's a very important piece of the network, because if the firewall's not working, the network's not working. Leslie, in her comments yesterday, mentioned the first quarter, all the grief and people calling, that was the legislature calling, because we were having some problems in the TCP IP stack and the firewall and this interlink controller. So, and legislature was using this. So it was a lot of problems, and I was new on the job, and when you get the call from legislature, you get kind of, especially on a Friday night. But firewall, we use something called right now a Raptor firewall. Raptor. On the IBM technology, we're converting to a Cisco firewall called a PIX, P-I-X. And over here on the mainframe, we have a TCP IP stack that talks to VTAM, that talks to the applications. That's how TN3270 works. That's TN3270, a TCP IP protocol to allow you to look like a 3270 terminal and talk to an SNA mainframe that has a TCP IP stack. Another protocol within TCP IP is called FTP, File Transfer Protocol. It allows you to get and put files. Get. We log on to another computer, and there's a file there that we want, so we get it. We make a copy of that file down on our computer, our PC or our enterprise server. Now you can also, within File Transfer Protocol, do puts. Take a file from your machine and send it to someone else. Gets and puts. FTP is very efficient. It's very fast. People who have converted from it, from other techniques, there's a 3270 an SNA called IND dollar, which is kind of slow. They convert to FTP and they just can't believe it, how fast it is, because of the link speeds and how it operates. The hardest part of FTP is getting it set up the first time. The first time is tough. But after you got it working, it works like a champ. It's great. So FTP, File Transfer Protocol, how we can exchange data files between computing systems. Another protocol that we will talk about is SMTP, Simple Mail Transfer Protocol. What's that? Well, it's this common standard that allows you to send email to anybody. In other words, here we run Microsoft Exchange. and I sit down at my terminal and I want to send an email up to a guy named Jeff Crowder at Virginia Tech. So I say at crowder@vt.edu, and I compose it on Microsoft Exchange. And then I say send it to him. Well, what happens with that? Well, it goes through some mail servers that convert it to this common format called SMTP, Simple Mail Transfer Protocol, ships it across the network to VPI, where a mail server receives that SMTP, because now it's in a standard form, and converts it to whatever email system they're running. So it is the vehicle that allows us to exchange email without having to care or wonder about what email system they were running. If it weren't for SMTP, and before we had something like that, you know, if you were on your own private little email system and then you wanted to send something to, say, somebody on MCI, couldn't do it. There was no interoperability. SMTP is a vehicle that allowed that interoperability, so when we can put mail in a common format and exchange it between mail systems. The last protocol we're going to talk about is something called HTTP, Hypertext Transfer Protocol. Hypertext Transfer Protocol. That's what the HTTP colon, that's what that stands for. It allows a network computer to listen for and respond to requests. What kind of request? Well, requests for web pages. It is part of the essence of the World Wide Web, the WWW. Now, WWW does not stand for World Wide Wait. Okay? I know sometimes it seems that way. I was looking for something this morning, did a search. I was going through, finding things, you know, I'd wait 5 or 10 seconds. Well, I ain't going there, stop, go to the next one, forget that. You know, we get so impatient. But, you know, considering how these things are, how, you know, we've got the maze and the regionals and the ISPs and all these networks, considering that this thing actually works and comes back in seconds is really kind of amazing. A little history on the World Wide Web. It was released, actually, the definition for it was released in 1991 by CERN, European Center for Nuclear Research in Geneva. It really took off in 1994. It took off because of the availability of browsers. The first browser that was widely available was one called Mosaic. Probably never heard of a Mosaic, it's all gone. The guys who were at Mosaic formed Netscape. Netscape was the browser that really got the internet going. Now, I love Bill Gates and all that kind of stuff, but Internet Explorer was a Johnny-come-lately. You know, Netscape was there and doing it before Internet Explorer and Microsoft was there. Okay? But, you know, Netscape and Internet Explorer are very comparable browsers. It uses something, the World Wide Web, called a URL. My doctor asked me, he said, what's a URL? And at the time, I didn't know. It's a Uniform Resource Locator. It is an internet address for a web page, like that. That's a URL. That's our URL. And it's composed of a domain name, this part here at the end, state.va.us. And the hierarchy is it works from the right back to the left. The last part defines the organization, like US is states, COM is commercial, EDU is education, GOV is federal government. I don't know why they won't let us be government too. US is states. There are other ones. Those are the common ones. There are others within the United States. If you see ones like UK, that's United Kingdom. Countries, other countries generally end with their country. AU is Australia. I think CA is Canada. Okay? So we back up here for a minute and you say, wait a minute, Charlie. What's going on here? You told me all this stuff runs on TCP IP and it all works on IP addresses, but yet you say that the internet address for a web page is that. Well, that doesn't look like that, you know, number, dot, number, dot, number. Doesn't look like that. So you know, what goes? Well, we have a browser. Now, an example. We all have social security numbers, right? What if we had to talk to each other and remember each other's social security number? You know, we're not good at remembering numbers, especially 9-digit numbers. So we have names because we're better at remembering names, some better than others. So, in the World Wide Web, we use names as opposed to IP addresses. Now, if you know the IP addresses, if you're a diehard and you know the IP address, you can type an IP address up there on your web browser, and it will actually be a little faster. But, you know, who remembers IP addresses? Certainly not me. So, what happens if we type in www.state.va.us? And I was so happy when they made it so you didn't have to remember that //h, you know, never could get that, you know, which is first, where's the colon, where the slash is. So it was really nice when they, you know, developed it so you could just type it like that. So what happens? So, you know, we type this name. How do we get an IP address out of that? We get it through something called a domain name server, a domain name system, domain name server. Your browser has within it an IP address that points to a domain name server. So if we want to send something to www.state.va.us, our browser looks within itself and says, do I know the IP address of this? Because it has a cache within itself where it's looked at things that it's been to before. And it says, no, I don't know the address of that. So it sends a request to a domain name server. And the browser knows the IP address of where that domain name server is. Here's our domain name server, and it sends it state.va.us and says, where is this? What's the IP address of this? Our domain name server keeps a table of those things. It looks it up. If it can't find it, this is another one of those deals where, okay, well, there's another domain name server someplace. Maybe that one knows where it is. And there is a hierarchy that it will pass this name up the line, trying to resolve, this is called a resolve process, resolve to an IP address. If it is successful, it will convert that URL name to an IP address and pass it back to our browser, who will then send a request to that IP address for the web page, and we get that. That's how it works. And now, you know, when you see that, you say, well, gee, maybe I shouldn't be so impatient when it takes 5 seconds, and, you know, stop, let me go someplace else. Why is it so slow banging on the desk? Okay? Because that's the process it goes through. Well, how are these web pages constructed? They're constructed with something called HTML, Hypertext Markup Language. It is the language used to build web pages. It uses tags to control appearance. Tags. What's a tag? Well, here's an example of some HTML. It uses these less than and greater than symbols to bound the tags. And then they're in pairs. So this says, what follows this I want to be bold. B stands for bold. And then anything from that point until there's a corresponding tag with a slash in that same tag, this says stop bolding. So that's how bolding's done. Bold, make something bold. You can put italics, you can do all sorts of things. You can set the font size, you can set colors. Here's an example of some HTML. If you take this, the browser converts the HTML into something that's viewable. That's the job of the browser. If you take this code and send it in the browser, you get that. That's only part of the code. There's actually more of it. Hey, if you want to see HTML code, if you go up there and click View, it'll say Source, View Source, and you click on that, it'll show you what the HTML code looks like. This is what people are writing when they're building web pages. And you say, you know, gee whiz, you got to remember all those little tags and stuff and do all that? Well, there's some great web development tools out there. There's one called Front Page, one called Coffee Cup. One that I use is called AOL Press. It's free. I like the price. And it's a good little web development tool because it's a WYSIWYG. What you see is what you get. You kind of paint the screen, and it writes the HTML. If you're interested in learning HTML, there are lots of courses around. If you want to learn give me a call. I have a little tutorial that I downloaded from the web. It's how I learned HTML. And this, the guy who wrote this suggests that you learn HTML so that you know how it works, and then forget about it, get a web development tool, and build your pages that way. If you have an ISP, they probably provide you space where you can have your own web page. I mean, and that is the thing now. If you don't have a web page of your own, you know, you're nobody. If you don't want to pay for a web page, there are some free places where you can get free websites, one called GeoCities, where I have my high school web page. It was the reunion, not like I just graduated. Okay, so what did we talk about today? Talked about a lot. We talked about TCP/IP, Transmission Control Protocol, Internet Protocol. We talked about IP addresses and dotted decimal. Talked about routers, Cisco and Bay. Talked about the Internet, May East, May West, all those little Mays, ISPs, regional networks. We talked about another part of TCP/IP applications, Telnet and TN3270. Talked about File Transfer Protocol, FTP. Talked about SMTP, Simple Mail Transfer Protocol. Talked about the World Wide Web. And we talked about HTML. Gee, I have 6 minutes. And someone is clairvoyant here, because they made a comment to me when I was coming upstairs, and I'm going to show, this was already there. They said, are there going to be fireworks at the end? And there are. I swear, somebody in the hall said that to me. Are there any questions? Toby.
For the high-speed access lines.
The internet service providers, well, you and I do. They used to be from National Science Foundation, but they've pretty much gotten out of that. Now this May East and May West, they sell their service to the internet service providers like the AOLs and the Arrows of the world, so that's how they're paid. And then you and I pay the internet service providers if we subscribe to them. Other questions? Charlie?
What keeps the whole internet from collapsing under the increasing weight as more people sign on?
What keeps it from collapsing? Well, last year that was a real issue because it was on the verge of collapsing last year, and there was some really serious problems and some really serious slowdowns within it. But the people at WorldCom and the carriers and the people who run those networks have kind of stepped up to things and increased the capacity on it. But, you know, it's like they're always a step behind. So they're continually adding capacity, trying to catch up. One of the things that's very, very big that I'll mention very briefly since I have 5 minutes is that's very big in the internet now on IP, which is going to really be a problem for the internet, is doing telephone calls, voice calls over the internet. This has been around for a couple of years, and there were some packages out there from some companies, and you had to have the same software at both ends, and you had to have some special hardware and all that stuff. It's advanced quite remarkably, and there are lots of people. In fact, there are people in this room who do long-distance phone calls through their internet service provider. The quality has gotten pretty good. It's not great yet, but it's getting there. And this is a very hot topic now. And people tend to believe that voice phone calls, especially long distance, will move to the internet. Now, voice, the sampling techniques and the compression techniques have gotten better, but voice is a very data intensive because you're doing samples, that analog, sampling it, putting it in a data form, in a digital form, transporting it across the network. It's very intensive in terms of the bandwidth. So when something like that happens, it's going to could cause a lot of problems. You can also see television. You can do video conferencing. My own little, I think within the next probably within the next 3 to 5, certainly within 5 years, probably 3 years, you're going to see, I believe, the integration of your telephone into your PC at work. You're going to have a little video camera on there. You're going to be able to click, you know, when you want to talk to somebody, click and it'll send them a request, and then they may or may not answer, and then you're going to on demand have a little video conference there. So rather than walking down the hall, you're going to have a video conference right there through facility. I mean, we're this close to that. The telephone is going to be part of your PC. Let me drop back for just a minute. Last week I mentioned that about if you wanted to know about video conferencing, to see Stu Thacker. Stu Thacker was the father of video conferencing here at DIT, but it's now become a mainstream product service offering. So you want to talk to Ann Hardwick or Dorothy Boland, and they have some neat facilities down there, and they'll be happy to show you what they've got and how video conferencing works. So within the next, I would say probably 3 years as opposed to 5 years, the only thing that kind of changes the equation is the year 2000, because that kind of messes things up and you got to get things working. You're going to see that integration, and it's going to be a neat world. I mean, you can see it coming. Any other questions? I thank you very much. I have enjoyed it immensely. If you're interested in seeing the pre-show, which has all the names that I got from training, stick around. Thank you.